Now, last day we left off with this problem. Let me just remind you, we had a hand push that spring, compress that spring by ½ meter. Now, if that spring has a spring constant of 16,000 newtons for each meter, then the energy stored is going to be given by that formula, 1/2 times K times the compression squared. Now, the most common mistake on the next exam will be that square there. Many of you will forget it. Many of you will write it and not do it. Look at your neighbor right now and say, it's going to be you, not me. Okay? Now, if I take a half and square it, I get a 4. Half of a fourth is an eighth. An eighth of 16,000 is 2,000 joules. Now, that's the total energy of the system because the block's not moving and the block is on the floor. Now, we release the block and we asked how much kinetic energy does the block have when it gets away from the spring? The simple way to answer this is to say, hey, I had 2,000 joules and I didn't get robbed. I'm on a frictionless floor. There's nothing that's taken energy away, and so I must still have 2,000 joules, but now it's in the kinetic energy bucket. And that allows me to figure out how fast the block is going. If I now use the formula for kinetic energy, I have 2,000 joules of this kinetic energy. That's equal to 1/2 times 10 kilograms times the velocity, the speed at a squared. That gives me 400 is equal to the speed at a squared, and that gives me the speed at a of 20 meters per second. Easy. Now we get to the point where we left off. That block hits the rough place at B and starts scraping. And the question is, how far will it scrape before it stops? And with your neighbor, see if you can come up with an answer for that. How far will it scrape before it stops? Yes, sir. No, that wasn't a hand up. Yes, sir.
100 meters?
100 meters is the correct answer. Good job. Good job. Okay, let's do it together as a class, because some of you seem not to have gotten that answer. If I go back to our derivation that we did for the kinetic energy, we found that this combination of force times distance is what changes kinetic energy. We called it the viric. Now, if I replace those 1/2 mv squareds with just their symbol, I'm going to write this in a way that makes more sense, I think. If I take the initial kinetic energy and bring it to the other side of the equal, it becomes positive. And then if I replace the left with the right, it looks like this. Now, the way I read this is the kinetic energy in the morning is equal to the kinetic energy in the evening, except when it's not, and it's usually not. Now, in this example that we derived this formula for, we had a block on wheels on a level, flat surface. Now, there were no springs, so there was no spring energy possible. We called the height of that level surface 0, so there was no gravitational energy. The only kind of energy possible for this block was kinetic energy. Well, in most problems, you have different types of energy possible. And in those problems, we have to generalize this equation to that. We call that the Verk energy equation. And it's the one equation to rule them all and in the darkness bind them. Okay? And we read this again. The energy initial is always, always, always equal to the energy final, except when it's not. And it's usually not. Now, folks, here's the thing about energy problems. That's always the first step. If you were to take a blank piece of paper and write that at the top and Xerox it 20 times, you would have your stationery for the next week and a half. Every time you had an energy problem, you'd just take one of those sheets, you'd be halfway done. And that's the other nice thing about energy problems, is that's halfway done. Okay? All you got to do from here is decide what kinds of energy you have at the initial event and the final event. To do that, you just ask yourself 3 questions. Is anything with mass moving? If yes, you got kinetic energy. Is anything up off the floor? If yes, you got gravitational energy. Are any springs compressed or stretched? If yes, you've got spring energy. Now, what do I mean by initial and final? I don't know. That's up to you. You get to choose what you mean by initial and final. One of those should be a time when you know everything about the energy. The other should be a time when you're looking for information. Whichever one happened earlier in the day is the initial. That's it. That's all there is. And every single problem is solved that way. Let's go back to this problem. When this block got to B, it had 2,000 joules of kinetic energy. And then Verk happened. What kind of Verk? Negative Verk due to the friction. And that bled all the energy out of my bucket, and I was left with no energy. So I would solve that by starting with this equation. Energy initial plus Verk is equal to energy final. Now, initially, that block just has kinetic energy. There's no springs and it's on the level floor. So I have kinetic energy and I have 2,000 joules. The Verk is going to be negative because the friction force is acting this way while the block is going that way. So that's going to be minus the friction force. It's kinetic friction because I can hear the scraping going on. That's by the floor on the block times the distance. And that equals, when it stops, 0 energy. Now you can see if I'm looking for delta X, if I know the friction force, I'm done. Well, I've known how to find a friction force for a long time now. I draw a free body diagram. The weight of that block is 100 newtons. There's the normal force by the floor on the block. That's 100 newtons. And then there's this friction force. It's kinetic friction, so it's mu times the normal force. But these indices have to be the same. And so this is going to be 0.2 times 100, or 20 newtons. So if I come back here and I say 2,000 joules minus 20 newtons times X is equal to 0, solve for X, you get 100 meters, as this gentleman back here did. Okay?